Probando, probando. Hola, hola. Probando, probando. Uno, dos, tres. Uno, dos, tres.
Buenos días a todos, gracias por venir. Hoy tenemos el agrado de presentar a César Laia, de la Universidad Nueva de Lisboa. Él está haciendo una estadía desde enero de este año acá en Emisión, en el marco de un proyecto europeo de intercambio de staff, de científicos y tecnólogos de países europeos y de todo el mundo. En particular, el proyecto que compete, este logo que es BIT, trata de polímeros, que en particular se llaman bitrímeros, que son característicos porque tienen enlaces covalentes y además son muy utilizados porque se pueden reciclar, reusar y se autorreparan. Y esos polímeros pueden ser un elemento clave para lo que está impulsando la Unión Europea de la economía circular. Se pueden reciclar y el consumo de fabricarlos es muy bajo en energía. Bueno, César es doctor en fotoquímica en el Instituto Superior Técnico de Lisboa. Él se recibió de ingeniero químico, ¿no?
Sí.
También en la Universidad de Lisboa.
Sí, sí.
Y en el año 2000 hizo un postdoc en el Instituto Superior Técnico y en el Imperial College. También en fotobiología, o sea, es bastante afina a muchas temáticas que se hicieron en el CIOp durante mucho tiempo. Después se trasladó a la Universidad Nova, que es una de las universidades de Lisboa, que está en el sur de Lisboa, desde 2006 y es investigador. Desde ese tiempo trabaja en fotocromismo, electrocromismo, en materiales luminiscentes. Y en el año 2018 es profesor de la universidad, de la Facultad de Ciencia y Tecnología, que es el logo que se encuentra acá a la izquierda. Bueno, ha sido el investigador principal de distintos proyectos europeos y nacionales, y también pertenece, como les dije, al proyecto BIT de la Unión Europea. Bueno, hoy el seminario que nos va a impartir es Advancing Electrocromismo and Photonics for Intelligent Windows of Smart Labels. Eso, para traducirlo un poco, es un poco de lo que estuvimos en estos 2 meses trabajando en concentradores solares, utilizándose estos bitrímeros, y en la última parte se agregó un dopante de una molécula orgánica para hacer un shift del espectro del sol y ser más eficiente cuando se recolecta en una célula solar el espectro que absorbe el silicio. Bueno, lo dejo con César.
Gracias, Gustavo.
La charla va a ser en inglés, pero César entiende español, así que las preguntas pueden ser en español.
Sí, ahora voy a hacer en inglés, perdón por esto. Mi español mejoró mucho desde 2 meses aquí en Argentina, pero para hacer la presentación en español creo que sería un poco difícil y por tanto voy a hacer en inglés. Pero las cuestiones finales pueden ser en español. Yo, si consigo, intentaré responder en español también. Por tanto, gracias Gustavo por la presentación. Now I'm going to switch to English. Today I'm going to talk about two ways to do what we can call intelligent windows. One is one that I've been working a lot since in the last 20 years. It's called electrochromism. And then applying also photonics to produce what we can call smart windows. And because I have a collaboration with a Portuguese company, I will also briefly talk a little bit about smart labels. First, location. So, here, we are here in Argentina, in La Plata, and Portugal is the western country of Europe. So, it lies here. It's not the most western country of Europe because, of course, we have Iceland. but in continental Europe is the most southwestern country. So here is Portugal, and Lisbon lies more or less in the middle, next to the river Tagus. And here is the downtown of Lisbon, in which I have a picture in here. And the Lisbon airport is situated within the city. So this means that if you go to Lisbon and you want to visit downtown, you just pick up a subte and you arrive very easily to the Lisbon downtown. The university where I work for is located here in the south bank of the river, and you have here a picture of the building where I work. It's close to the sea, and to arrive here from Lisbon, you can either pick up a train that crosses the river, and then you have a train that goes to the faculty directly, or you can pick up a boat in here and cross the river to this point, and then you pick up the train and also goes directly to the faculty. So this is where I'm situated. And now let's go a little bit into the topic. Okay, like Argentina, Portugal is also a very sunny country, especially in the summer. Our summers are a little bit different from here because they are extremely dry in July and August. It doesn't rain, which of course is better because then you don't have the plagues of mosquitoes. But it also means that Portugal becomes brown during the summer because all the grass dries up and the landscape is brownish in August and September. So we have many problems regarding water because water supplies must be replenished during the winter, but we also have a lot of sun. And like in here, we are experiencing more and more heat waves during the summer. And so air conditioners are now becoming something that is extremely important to have in our homes. So how can we decrease this demand of energy to air conditioners? How can we keep the houses fresher? That is the central point behind the applications of intelligent windows. So one application of intelligent windows are the so-called electrochromic windows. So electrochromic windows uses electricity to darken the window. The concept appeared in the late 60s by that, and during the 70s there was a huge jump in terms of technology that was investigated mainly in companies. And so during the 70s there was this dream that you could make electrochromic windows that could be darkened when the sun was too much intense, and so keep the room fresher on one hand, and that in the other hand also with not so much light. However, after these technological jumps in the 70s, then in the 80s, this technology become a little bit stale, and you will need to wait for the 90s to have next jump in terms of technology when the semiconductor polymers arrive to the picture. Now everything is well developed to the point in which you can purchase from this company called Sage Glass electrochromic windows. This Sage Glass is part of Saint-Gobain, and so they exist and can be used. Another example of intelligent windows are the so-called thermochromic windows. The best example that I know about the application of this technology is by a company called Intuitive that build up these windows that becomes darker when temperature increases. And it is a very interesting technology. It works very well. But from what I know, after the pandemics, this company is suspended. It didn't close, but it's not operating. I don't know if they are going to come back online again, but they stopped during the COVID breakout. So this type of windows changes color with temperatures. And then you have another class of intelligent windows that are the so-called luminescent solar concentrators. So, for just an example, you have here a greenhouse, and this greenhouse has these luminescent solar concentrators, which I'm going to explain afterwards, that will harvest the lights of sunlight, and then the sunlight is guided to the borders of the window where you have photovoltaic cells. And the greenhouse is a great example because you have a lot of glass sheets all over the place, and so you can collect indeed a lot of sunlight. And here it displays one case in Australia in which they measure the quantity of energy in watts per hour between May during 1 year. So there is Australian winter in here, then summer, and so on, all around 1,500 watts per hour. So this is the concept of another type of intelligent window, and I will go a little bit more on this. So in the first part, I will describe the part of the research with electrochromism, and then in the second part, I will go into the part of the luminescent solar concentrators and discuss what we are doing with here CIOp and also in TEMA concerning the European project VIT, that's why I'm here. Okay, electrochromic devices. Okay, electrochromic devices might sound peculiar for you, but remember just this. Electrochromic devices is just like a battery, okay? So the architecture of an electrochromic device is like a battery, but it is transparent. So this is the big difference. What is an electrochromic device? Is when you can change the redox properties of a given material, and when you change the redox, if it is reduced or oxidized, you change the color. Okay? You can argue, okay, but that is known from almost more than a century. But it was only applied as a technology in the late 60s, as I said before, because this must be completely reversible and make as many cycles as possible. So, what do you need? So, you need a substrate that in this case must be transparent to see the color. Then you need a conductive layer. Typically, it's IPO, which you have in all your smartphones. So it is transparent, but it can conduct electricity. Then you have your electrochromic material in here. You need an electrolyte layer, just like in batteries. And then you have a counter electrode that in this case, it mirrors exactly the electrode above. And so if you oxidize this part, you reduce this one, and the other way around it happens too. And so you can change color as much as you wish by this way. Our first, about the materials. In terms of substrates, you can do it in many different types of substrates. The usual ones are glass and plastic. However, we already did in materials like paper, cork, wood, even concrete. Okay? In terms of the conductive layer, the classic ones are ITO or FTO. But it can also be semiconductor polymers, or it can be graphene sheets deposited over, or even carbon nanotubes, whatever that can conduce electricity. It must be transparent, however. So these films must be extremely small in terms of thickness. Then the electrochromic materials. Typically, you have metal oxides, semiconductor polymers, organic molecules, ionic liquids, and the list goes on and on, since the variety of electrochromic materials is increasing every year. The electrolyte layer, usually it is a polymer matrix, for instance, polymethyl methacrylate, with an electrolyte like lithium perchlorate, an ionic liquid, whatever you can put that it's going to give the electrolyte that you need for the device to operate. And this is the general sketch of an electrochromic device. So, we began earlier than this, but a breakthrough within our research in this area was achieved by Claudia Costa in the 2012 while she was doing her PhD. So Claudia worked out ways to make metal oxide nanoparticles of tungsten and vanadium, and these nanoparticles could be deposited in PET plastic ITO electrodes, and so we build up these electrochromic devices that were published in the 2012. And here are two examples with nanoparticles of sizes 200 nanometers and 65 nanometers. This was a while ago, already about 12 years ago. And meanwhile, Claudia Costa moved on, then she did a postdoc and now is working in a Portuguese company in the research and development facilities of that company. I still collaborate with her. Then, organic polymer nanostructures. So, semiconductors, polymeric semiconductors appeared in the late 70s. And of course, in 2000s, these people gained a well-deserved Nobel Prize for that. And the development and the studies, especially done by Alan Meager, of the physical-chemical aspects of these semiconductors, was huge during the 80s. But only in the 90s, these polymers could be used as electrochromic materials. And the polythiophene are the good choices to make electrochromic materials. The most used polymer is this one that we call PEDOT, and it has this structure. It is industrial produced by Bayer, and so you can buy these in large quantities, and so it's very available. Then you have other types of polythiophenes, like this one, in which you have here an axial group attached, and the colors will be different depending on what you decorate in this region. So, Tiago Moreira, a former PhD student, because he finished in 2022, I guess, his PhD, worked especially with this type of polymers, and through a European project, we start to study this specific polytyping that we call P3HD. Okay, how does it work? If you have the polymer in a neutral form, then you have the conjugation of each monomer that will lead to what we can call a pi-pi star electronic transition. And so you get this neat electronic transition that will give the color of this polymer. If you oxidize, however, the localized excitation or the exciton is going to be electrostatically attracted by the positive charge, and so this level of energy decreases and produces two different levels of energies that we are going to call polarons. Polarons 1 and polarons 2. The consequence of this is that the absorption spectrum, because now you have these electronic transitions, is pushed into the near-infrared region, while the absorption of light in the visible region decreases a lot, and so the spectroscopic of this material changes. Also, the color decreases because the color in the visible region disappears. It appears in the near-infrared region. What we did was to work out with Italian colleagues from Bologna, because we had the technology to make the polythiophene nanoparticles, and these nanoparticles could be produced in water, and so we could deposit this polymer as a water dispersion. This was opposed to the usual technique in which you deposit it in an organic solvent like chloroform. So, in terms of sustainability, it's much better to use water, of course. So, the technique that we describe with some detail on this book chapter is the nanoprecipitation method. So, you have here we have water, and you need to stir it. Then you have the polymer dissolved in a good solvent, like for instance THF, which is completely soluble in water. So, good solvent, bad solvent in here for the polymer. You start to inject the droplets, and with the stirring they are quickly dispersed within the water, and the polymer chains collapse. And so they will make spheres, and you create the nanoparticles that will be suspended in water. And this is a very straightforward method. Then you have polydispersed nanoparticles, but if you do centrifugation, the bigger particles will deposit in the bottom, the smaller particles will be on the upper part. And if, depending on the rotation of the centrifugation, you can get in the supernatants different type of nanoparticles, different sizes. And so we can create nanoparticles with sizes like, for instance, 100 nanometers, 200 nanometers, and 400 nanometers that we measure by dynamic light scattering and by SEM. These particles were studied in the cyclotron as well, and they displayed some crystallinity features. So actually they are polymorphic, they have amorphous and crystalline features in the nanoparticles. We believe that most crystalline part is located in the core of the nanoparticle. In terms of spectroscopy, so what we have here is the absorption spectra of the polymer in chloroform And it is a good solvent, okay? So you have a neat pi-pi transition in here, and then you have the fluorescence, which is quite high. It has a very high fluorescence quantum yield in chloroform. But as soon as you do the nanoparticles, you start to form aggregates. And the aggregates appear as these shoulders in here, which technically are called the J aggregates. This has an impact because the fluorescent intensity decreases a lot, so the quantum yields become extremely low, and in some cases the fluorescence disappears completely. And the Stokes shift also increases, it increases not so much because we have here, what changes a lot is the band gap. So the band gap becomes much smaller. Okay, so we characterize the nanoparticles, then we make the deposition to characterize the thin films. And now, when you do the thin film from the polymer in chloroform, it matches very well the spectrum of the nanoparticles that remain fairly the same as in the suspension. With the thin films applied like this, we could measure a lot of stuff, like the band gap, it remains fairly constant, and the HOMO and LUMO levels of this form of polymer, which also remain fairly constant. Now, when we do the electrochromic device, what you see here is the change of color as we apply electric potential. And in here, it was the jackpot, I could say, because this is the thin film, and the thin film, yes, it shows some difference in color. Here in the near infrared region increases, but you can see that it doesn't change a lot in the visible region. With the nanoparticles, probably because we will have an interfacial area that will be much bigger than in the thin film, what happens is that the oxidation of the polymer is much more effective, and so you get a bigger color change. A bigger color change means a better color contrast. And yes, these photos just show that the contrast is really big. In here, I hope the video appears, as it is a little bit upside down, but it's okay. These are the thin films, these are the nanoparticles. You can see already the intensity of the color, and the switching is much faster when you have the nanoparticles. Okay? So, again, another color change. And so you have this color change that are extremely fast with nanoparticles and much slower with the thin films. We analyze this, and not only the color contrast is bigger, but also the switching times are smaller, so the device is faster, and most importantly, the durability of the device increases a lot when you go from thin film to nanoparticles of 1 nanometers. Then if you increase the nanoparticle size, then the durability decreases again. Okay? So we have a neat point with 1 nanometers particle size in which not only we are using water instead of organic solvents to make the deposition, but also the device works better. Okay, but this polymer was well known, and we wanted to play with polymers that could be new. And so, with our Italian collaboration, we started to synthesize big variety of polymers. And one interesting thing in here is that you can classify all these polymers as semiconducting polymers, But in this special case, which is the polymer 6, in here you don't have conjugation, which means that the electricity cannot go from here to here. So this technically is not a speed conductor polymer. We did it anyway. Why did we do this polymer anyway? Because red color and blue color exists and are easy to make in electrochromic devices. But there is one color that is particularly difficult to do, which is the yellow. And so we try to achieve the yellow by breaking the conjugation in here, hoping that it still works as an electrochromic device. Here are some numbers, okay? Briefly, the fluorescence quantum yields in chloroform are always high. In one case, it reaches 35%, which is quite good. If you put in a more rigid media, surely it will go above. And then we did some theoretical calculations. Now, if you have the conjugation, you have the HOMO-LUMO transition happening at a wavelength close to 530 nanometers, which will give the red color. That is easy to achieve. But if we break the conjugation, then what happens is that you have the HOMO in here, and then in the LUMO you have a charge transfer for the other part. And this will produce an electronic transition that is now around 430 nanometers and brings the yellow. Okay? So at least yellow color could be achieved with this polymer 6. And here it is, the polymers, different polymers. So these polymers also produce the yellow color. The problem is that you have to apply potentials that are too high for a device, because then it starts to react with the ITO that you have there. But with this polymer 6, we indeed produce the yellow color. The only difference is that instead of having electronic transition from yellow to one color, now we have an electronic transition from yellow to black. Okay? Because then the near infrared part counts into the visible region. And then we did the nanoparticles as well. And again, the nanoparticles behave better than the thin films. Here is the same image of the nanoparticles. And we got a very nice contrast for the nanoparticle devices. And I believe now I have a video. These videos are recorded with the digital camera, and so many times the colors are a little bit mixed up. But believe me that here in the inner part, this is a yellow and not an orange. Okay. And now this technology, of course, can be applied because we are using water. And the proof of concept was done in the laboratory. The next step will be to jump to upscaling this. And that's another story because that requires collaboration with industry. Okay, about collaborations with the industry. We have a collaboration with a company that started in our campus called Invisible, and now actually technically it's not a Portuguese company because the headquarters is now in Toronto, Canada, but it still has a lot of facilities in Portugal, in Germany, and Sweden. And they are working in electrochromism to make electrochromic labels. Okay, so in this project, what they were looking for is a countersense. So when we have electrochromic devices, you want them to be reversible. But the companies started demanding exactly the opposite. Companies that want to work in safety, for instance, want that scholar change to be irreversible, that you cannot go again to the initial state. And so this irreversible electrochromism seems to me something very easy to achieve. If you reduce sugar, you produce caramel, so it is a color change, irreversible. But actually, to control this type of things is extremely difficult. And so, to make something that will be in accordance with protocols of safety, you need to play with chemistry. And so, this PhD student, Ellen Howard, that we hope she will defend the thesis in April, enrolled in this project in collaboration with Invisible. And what we tried to do was to make a label in which a monomer of thiophene is electropolymerized to show a message saying, for instance, that these goods were damaged, or that temperature was suppressed in the transportation, or whatever. Okay? And indeed, she did a lot of work with this and tested several formulations, especially of the electrolyte. And for instance, in here, you can check out that when you apply 3 volts to the label, it really goes from white to black in about 5 minutes. Okay? And this is a huge color constraint, and then it can be used as an irreversible visual indicator, and it's part now of the portfolio of the technology owned by this company. Okay, enough of electrochromism. Let's go now to the luminescent solar concentrators. That's the part that brought me here to CIOp. And first, let me explain what is a luminescent solar concentration. So, you have a dam. When you have a dam, this part is the harvesting of water, and then this part is the conversion of the gravitic energy of the water stored in here to electricity. So, you need first to harvest, and then you need some device to make the conversion. So this is the principle. Okay? This principle exists also in nature. If you look into the photosynthetic center, you have an array of chlorophyll molecules that can absorb light. And then the excited state energy can be transferred between neighboring chlorophylls until it reaches the reaction center in which the actual photosynthetic reaction will happen. And so you have a larger area to collect photons, you get a better photosynthetic yield. So this concept exists, and the luminescent solar concentrator, in terms of concept, is exactly like this. When we're talking about energy, we are talking about 4 steps. You need energy harvesting, you need energy conversion, then you need energy storage, and you need also energy distribution. Of course, I'm not going into the energy distribution. It's a power grid, it's gasoline stuff, whatever. Energy storage could be fuels, could be batteries. I'm not going into this as well. What I'm going to talk about is the energy harvesting and the energy conversion with the luminescent solar concentrators, but especially in the energy harvesting. We have to bear in mind that when we are doing this kind of stuff, several aspects come into play. Economical, it needs to be profitable. environmental, of course, because we are doing this, we justify this because we want to save the environment and reduce the emissions of carbon dioxide. So this is a big goal. Safety, okay, so safety is an important issue because, for instance, nuclear plants can have economical and environmental benefits, but then it raises safety concerns, okay, and cultural factors. And nuclear power plants is a good example because usually people are really resist nuclear power plants. But it's not only that, even dams can have huge cultural factors because entire areas are flooded, including small villages. So all these aspects must be considered when you have this. Now, what luminescent solar concentrators can bring to this part? If you have light harvesting and energy conversion in windows for buildings, you will produce electricity in each window that you have in your home, okay? Without the need of distribution, so it avoids the power grid. It will be safe for humans and the environment because it just stays there. And this is the concept of micro generation of energy, which is also an opportunity for our undeveloped countries, especially very large countries underdeveloped, in which the power grid doesn't reach all parts of the country. So you micro-generate in your location energy that you need to do some stuff. Okay? The concept of luminescent solar concentrators appeared in 1960 in a work by Richard Garwin. This is a very small paper, just 2 or 3 pages in the Journal of Chemical Physics. And he introduced the concept of having some luminescent medium that would receive solar radiation, and then the light would go to a photocell that would convert the light to electricity. So this was the concept, and by 1976, again in the 70s, a lot of work started to appear regarding luminescent solar concentrators. However, again, the concept died a little bit during the 80s to become again preeminent after the 90s. And this is a very important review by Michael de. The name is Dutch, so I'm not pronouncing it well. In his review, there is a review of what was made during the 30 years of luminescent solar concentrator research. Mainly, they were using polymethyl methacrylate. And then they used a lot of fluorescence dyes, different fluorescence dyes, to make the effect. So, luminescent solar concentrator works like this. You have some transparent medium, and you put something that will be luminescent. The solar radiation will reach the surface, part is reflected, part goes inside the matrix. This light inside the matrix will then produce excited states of the molecules that you have inside, and they will have fluorescence or luminescence. Then this luminescence is trapped inside the device. Some of it might escape, but most will reach the borders, in which then you can attach a solar cell to convert this light into electricity. So this is the concept of the luminescent solar concentrator. What you want to do is to pick up light here in UV, blue, even green regions, and then convert it to light in the red regions, especially the regions in which photovoltaic cells work better. Okay? This is the range that can go from 600 meters up to 900 meters, depending on the type of solar cell that you have. Requirements. You need a broad spectral absorption to collect as much light, harvest as much light as possible. You need a high absorption efficiency, large Stokes shift, high luminescence efficiency, and you need that the emission of light is resonant with the photovoltaic cell that you are using. So, this scheme, you have the sun, light goes in with this power, light is transmitted, some is reflected, and then some light, due to luminescence, is emitted in this border in here. Lossless. So this is the general equation. This is the optical conversion of the luminescent solar concentrator, and you have a lot of things going on here. You have light reflection at the surface, given by the Fresnel reflection coefficient. You have the Stokes shift. Stokes shift reduces the efficiency because the light is going to lower energy. Okay? But in fact, we need the Stokes shift because we want to reduce the self-absorption part, which is worse than the Stokes shift effect. You have the trapping efficiency, and you have also scattering losses. And this is the fluorescence quantum yield. This is the amount of light that is absorbed. This is the self-absorption. So these are the effects that we need to take into account. If you go to a real luminescent solar concentrator, you also need to consider the geometrical gain factor, in which this value is the surface area that collects light divided by the area in which you have the photovoltaic cell. Okay? If the plane is very large, then the surface area will be larger, and so this G factor will increase, which in turn will increase the efficiency of the luminescence of the device. Okay? And this is also a way to calculate the optical efficiency of your system. We started to do perovskite quantum dots because it was a hot topic during that time, it still is, and they looked very easy to produce. At least in 2017, there is a paper in Journal of Chemical Education that seems that it is something very easy to do. It's not easy. We took at least 1 year to synthesize this quantum dot. It was much more trickier because it's easy to produce the quantum dots. The problem is that, yes, you have luminescence very bright for 30 minutes, because then they have the degradation and they disappear. Okay, so to make stable quantum dots was a real challenge. But anyway, if you change the composition of this quantum dot, you can go with emission from the violet till the red. So you can cover a big spectral range with this type of materials. Then Anna Pinheiro, which today is not here, but she will be here next Monday, synthesized these quantum dots, the poor girl, and after a big struggle, she managed to produce these ones with green fluorescence and with a very acceptable fluorescence quantum yield of about 72%. This is the luminescence decay, which is highly non-exponential because we have a mix of types of quantum dots. and crystalline structures that we could investigate by then. It doesn't matter anyway because we are trying to produce luminescence or concentrator and not a very well-defined quantum dot. And so our first test was to use nanocrystalline silicon photovoltaic cells. We covered this with the quantum dots, and by vapor deposition, we deposited this polymer to stabilize the quantum dots above the photovoltaic cells. And then we could make comparisons between uncovered and covered photovoltaic cell. So this, for instance, is the photovoltaic cell without the quantum dots, and this is the photovoltaic cell with the quantum dots. Immediately see light absorption in this area increases, and the efficiency has an incremental improvement in this region. And in this region also there is an incremental improvement. It's not huge, but it is promising. Here is the luminescence. In fact, when we do the encapsulament with the parallel, the emission shifted into the blue, but the emission looked quite okay. This is the 3D spectrum. We have excitation and emission spectrum, but in here you have the emission spectrum, and the transparency of the material was good. So we did also XPS. I'm going to jump this part. In the end, we could check that the efficiency of the solar cell indeed improved when we put the quantum dots with the parallel coating. Still not a luminescent solar concentrator. Okay? Now, let's talk a little bit about glass. Glass is a form, it's a solid that retains the long-range order of a liquid. Basically, this is a glass. While in a crystal, you have very well determined positions for the atoms within the matrix. Now, glass is important because it's amorphous and becomes isotropic and transparent. And it is characterized by a melting point in which you can go from liquid to a crystal, but if you cool fast enough, then you go below a temperature that we call glass transition temperature to produce the glass. Now, you have glass made of tough silica, which is in all our windows, and if you determine the viscosity as a function of temperature, you get this Arrhenius plot, which means that viscosity decreases in a very smooth way. And this has a very big advantages in terms of glass technology. It's much easier to mold the glass. You can make sculptures with glass, whatever you want with glass. Now, these are called the strong glass formers, because then you have the weak glass formers and or fragile glass formers. Polyethyl methacrylate falls within the category of fragile glass formers. What happens? Viscosity drops abruptly with temperature. Okay? And so they are not so easy to manipulate. And in this picture you have the landscape. You see that in a strong glass former, you have here a minimum of energy and you have the minimum of energy of the crystal, but it's quite well behaved. So if you cool fast enough, you avoid this trap to form the crystal, and you have here a very stable amorphous material. While in a fragile glass former, you have many traps, different traps, that can make these barriers smaller, and so the fragile glass formers are more difficult to manipulate. And remember that polymethyl acrylate is a fragile glass former, and it is used to make luminescent solvents. What we want to do is to replicate what happens with silica. So with silica, you have covalent bonds between silicon, oxygen, and silicon. So this is called bridging oxygen between two silicon atoms. Silica has a very high melting point, around 1,800 degrees Celsius. To decrease this, you have, for instance, sodium, and then you produce the so-called non-bridging oxygens that basically it decreases the melting point to around 1,200 degrees. So the temperatures that we are talking about in silica glass are in the range of thousands of degrees. In principle, there will be advantages if we use organic material. Why? Because these temperatures will decrease dramatically. And so, up to 2010, no organic strong glass former was known. Vitrimers are the first material discovered that can behave as a viscoelastic fluid. And this is quite recent, so it's about 10 years old, the technology of vitrimers. The change of the viscosity of the vitrimers follows an Arrhenius relationship with increase of temperature. So it's very different from conventional organic polymers. And you can shape it in the ways you want, you wish. So vitrimers have this advantage. Besides this advantage, they can have self-healing properties, a thing that normal glass doesn't have. It has shape memory. It can form, of course, composites, and as Gustavo mentioned in the beginning, you can achieve the circular economy, in which you have a complete recycling of the material and the end of the life of the device. Example, some chemistry. I know that most of you are physics, okay? I try to explain this as simple as possible. So, you have this molecule, and then you have this molecule. This oxygen here attacks this position and makes this bond. Okay? And when it makes this bond, what happens is that you get a bigger molecule. And this reaction goes on and on until it becomes very, very big. Then you have a second type of reaction. Oh, it doesn't appear. This, for some reason, it's not appearing in here. If you have a called equilibrium esterification, in which this oxygen now attacks this position, and this is crucial because it will make a three-dimensional structure that is amorphous. Okay? Also, this chemical reaction in here is reversible. So it can break or form this bond depending on temperature. And this is very important because this replicates the properties of silica glass. Now, if we want to do luminescent solar concentrators, what we need to do? We need to put something that is luminescent in the vitrimers. So, in our department, Professor Paulo Branco has been developing this kind of chromophores that have this, and one particular chromophore grabbed my attention, which was this one. It has an absorption spectrum that matches very well with the maximum power output of the sun, and then the light emission falls into the infrared. Okay? Or you can have something that is not so drastic and falls around 600 nanometers, in which you just don't have this group, but instead you have this group. So we are currently synthesizing these compounds, in special this case, what happens is that the electron goes from this nitrogen to this group in here. It produces an extremely large change of dipole moment, and that's why it has a very large Stokes shift, and it pushes the emission to the near infrared region. This part in here is quite flexible, which means that in solution, these molecules have low quantum units. However, we are working in extremely viscous materials, so that shouldn't be a problem. So, right now, we have synthesized this molecule, and work is being carried out in Portugal by this undergraduate student with the supervision of this PhD student to synthesize all the other molecules. Another molecule that we are using is this perilene, which has a very small Stokes shift, but a very large fluorescence quantity. Okay, why working with a small Stokes shift molecule? Because we are curious and we want to know what happens. Okay, anyway, the overlap region is not that big, so we hope that it will still work very well. And now, this is of course work in progress. This is something that we have been measuring in here to see the wave guiding with Gustavo, with some of these films. This is just one example. So it is blue excitation, and you can see the red emission all over the place, which is very nice. It was done by Gustavo and Ana. And Ana is now at ITEMA making wonderful objects like this, in which she's including the coumarins and the perinenes. So this is the coumarin, this is the perinene. I forgot to tell the names, sorry. What interests is that it has a very nice color, and then under UV light, it displays this. And in the latest developments, she made these bulk coatings between two glass sheets, and you can see the wave guiding of light in the borders very well. And so this looks very promising for luminescent solar concentrators. And so we are in the process not only of building luminescent solar concentrators, but also of making materials with different colors, which can be useful because you need to have the resonance with the photovoltaic device. And then we move on to make the device in which we want to irradiate with solar light, put a photovoltaic device, and then measure the quantity of electricity that is produced. So perspectives, we are working with deuteriumers to make these luminescent solar concentrators, and in my case, we also want to use deuteriumers as solid-state electrolytes for electrochromic devices. So this is also something that we will be pursuing. Acknowledgements. For the first part of the work, I have to acknowledge all these people, especially the PhD students like Tiago is not here, but like Claudia Costa and Tiago Moreira, and all the collaborators like David Bonifazi, Laura Mancini, Antoine Stopan. And here is Austria, but actually they were in Namur, Belgium, then in Cardiff, UK, and now in Vienna, Austria, so they are always moving. Francesca Di Maria, especially in Italy, and Professor Giovanna Barbarelli, which sadly passed away in the beginning of this month. She was already with some age. Paulo Samori in France was also important. It was work that I didn't show in here, but it involves the coating with conductive layers, but I didn't have time to show here. And now, concerning the big project, I have to point out, of course, Ana Pinheiro, Professor Paula Branco, which is helping a lot in the synthesis of this chromophore because she's an organic chemist. José Serrat and Tomé Souza is working, they are synthesizing the molecules. And a special mention to Professor Jorge Parola, which was here for the first month with me. Now he's back in Portugal. Of course, Gustavo and Cristina Hopp at Intema that is helping a lot to do the vitrums. And we still have this collaboration with Davide and Laura. Funding. A lot of European projects, Decochrome and Infusion, these are close, these two projects. Charisma project, it's almost closing. It's in the final part of the project. It was a program to make PhD students that worked in the industry quite successful. Ellen Howard was one of them. The VIC project, which the project that brought me here, and the laboratory that supports me back in Portugal, which is LA2V, with national funds. Okay, I hope I was not too long. I was too long. But eu creio que agora podemos falar em espanhol, se tiver.
Se pueden varias. Se pueden varias.
¿Tienes que hablar?
Se pueden varias preguntas.
Ah, claro, claro. Sí, muchas.
Cuando hacen la capa para el sustrato con las nanopartículas, ¿cuánto es el grosor? O sea, ¿han medido cuál es el grosor óptimo para que ustedes le hacen el
Okay.
para que haga el cambio?
Esse percurso óptico pode ser no tamanho que queiras, porque nós hacemos isso por spray. E, portanto, se hacemos um spray curto, o percurso óptico vai ser pequeno. Se haces um spray longo, tu aumentas a espessura desse percurso óptico. Isso é importante por quê? Porque necesitas de ter um percurso óptico grande para ter absorção de luz, para ter color. Okay? E é desta maneira que nós controlamos a intensidade da color.
Otra consulta, pero esta sí un poco más de conocimiento. Cuando utilizan las nanopartículas de dióxido de tungsteno, vi que que uno de los electrolitos era el perclorato de litio.
Sí.
Cuando utilizan ese electrolito, ¿tienen algún problema con la duración del dispositivo? O sea, el perclorato no te lo termina dañando en algún momento.
Perclorato es un problema, sí. Ok, estas coisas são proof of concept, provas de conceito. Em termos de durabilidade, esse não é um problema porque a durabilidade do material eletrocrômico e da parte condutora de eletricidade é menor que a durabilidade do eletrólito. Que, portanto, hasta ahora não é o maior problema. Pero perclorato de litio para algumas aplicações industriais não é ideal porque es nocivo. Perclorato puede ser explosivo. Por tanto, para aplicaciones industriales tienes que hacer un ajuste para otro electrolito. Pero yo colaboro con la industria, mas soy un académico, por tanto, esa parte creo que es una parte que tendrá que ser feita por la industria.
Y una pregunta en la parte química. Cuando hacen la sustitución con el dicarboxílico ácido, o sea, cuando hacen el polímero, después el ciclo alcano con el oxígeno, ¿tienen algún problema con la concentración?
Sí, claro. Sí. Era una cosa que nos contamos de intentar hacer los vitrímeros en Portugal. No estábamos a tener muchos problemas porque la cantidad de cada reagente tiene que ser muy precisa para que los vitrinos se formen sin problemas. ¿Okay? Y eso fue una cosa que aprendemos ahora con Cristina Hopp, porque tienes que trabajar con reagentes de gran calidad, con pureza muy elevada y con exatamente la estequiometría necesaria para ocurrir esas reacciones químicas. Porque si eso no acontece, los materiales pueden formar un vitrímero todavía, pero no van a tener las buenas propiedades de los vitrímeros.
Y con esa misma otra pregunta, porque es que me surgió muchas dudas con la reacción. Ustedes forman primero el polímero, o sea, me imagino que lo hacen en dos etapas. Una primera etapa de la formación del polímero y después otra en donde carboxila.
Eso va a ver.
Ahí.
Ok.
Yo,
Esta es la primera etapa. Tú tienes esa reacción que formas un polímero lineal. ¿Okay? Por tanto, este oxígeno ataca esa posición y forma esta ligación covalente y después otro va a atacar aquí, otro va a atacar aquí, otro y formas una cadena lineal de estos monómeros. ¿Okay? Esa es la primera etapa y ocurre en una temperatura relativamente baja, 100 grados. La segunda etapa tiene que ocurrir a una temperatura más alta, porque necesitas difusión de este compuesto de modo que ese oxígeno pueda atacar esa posición química aquí. Y entonces tienes que hacer una cura a temperaturas como 170 grados. Y produces una reacción que se llama transesterificación, en que ese oxígeno ataca aquí, agua sale y formas una ligación covalente. Y eso es necesario para producir la estructura tridimensional del polímero.
otra pregunta. Sí, porque en esa parte tenía dudas con la temperatura, porque si la suben mucho, no tendrían problemas con que se descarboxile y se te libere el CO2 del otro pedazo.
Claro, ese puede ser el problema, por eso tienes que controlar muy bien la temperatura y trabajar con monómeros que eso no acontece. Por tanto, es un problema para tener un vitrímero, pero es un problema principalmente para los corantes que colocas. Porque para muchos corantes, temperaturas como 170 grados ya es acima de la temperatura de decomposición. Por tanto, tienes que tener corantes que sean muy estables desde el punto de vista térmico.
Y una última, y ya aquí se me cayó. En la siguiente diapositiva, creo que. No, en la siguiente. Ahí. Tengo dudas. Cuando tú polimerizas.
Sí. Disculpa, perdón.
Cuando tú, en esta misma, o sea, si no entendí mal, tú querías polimerizar con los nitrógenos, ¿no?
Esos de aquí no son compuestos para polimerizar.
Okay.
Y estos son compuestos que ficarán disolvidos en la matriz polimérica del vitrímero.
Ok.
Entonces, aquí no queremos reacciones químicas, que es otro problema.
Claro, por eso te preguntaba, porque yo me imagino que si, o sea, que si tratan de evitar, o sea, un problema que pueden tener es que se les vaya el trato,
Sí,
porque esa posición está muy susceptible, ¿no?
ciertamente. Mas las experiencias que estamos haciendo ahora es con esta molécula que ya sintetizamos y trajimos para Argentina. No vamos a observar ese tipo de problema. Por tanto, pensamos que podemos seguir en frente.
Bueno, respecto a este sistema, el colorante de fluoróforo, ¿lo tenés en el vitrímero anclado o está
¿Anclado?
linked? It's linked to the
Ah.
vitrímero?
No, ok. Esa es una cosa que tenemos que investigar. En principio, esos corantes y este corante no van a tener reacciones químicas con la estructura vitrimérica. Pero algunas cumarinas que también vamos a estudiar tienen grupos carboxílicos, lo que significa que puede acontecer reacciones con los polímeros y ficar ancorados. Aquí tenemos que ser un poco pragmáticos. Lo más importante es que la absorción de luz es grande y la eficiencia es alta. Por tanto, si ficarán ancorados o no, es un poco indiferente en el final.
Pensando en posibles aplicaciones, sistemas sumergidos, que están entonces en la tecnología.
Sí, puede haber aplicaciones en que eso es importante. Sí, sí. Especialmente si quieres hacer reportajes de las microestructuras del vitrímero, que es otra cosa. Entonces, si tiverem ancoradas, pueden ser más sensibles a cambios de la estructura del polímero do que si tiverem simplesmente disolvidas en la matriz. Puede ser algo que podemos investigar más con el tiempo.
Con lo mismo, en el sistema de producción del polímero, cuando hacen la tres dimensiones, cuando hacen el sistema de tres dimensiones, pueden modificar la cantidad de ramificaciones para que esté más
Podemos.
compacto.
Eu mostrei um exemplo.
Que justo no sabía.
Eu mostrei este exemplo com essa molécula. Nós pode ser uma molécula com esta cadeia maior, ou pode ter, por exemplo, ácido cítrico que tem 3 carboxilatos em vez de 2. E com isso podes produzir vitrímeros com distintas propriedades. La TG pode incrementar ou baixar, a viscosidade pode ser diferente e, portanto, é algo que podes manipular para que pode ser muito importante para aplicações. La TG é uma coisa importante aqui, porque se produzes diferenças de color ou de seja do que for, pode ser um pouco malo para luminescent solar concentrated, mas pode ser bom se as diferenças de color são favoráveis para termocrômica, aplicações termocrômicas. Portanto, como são materiais novos, há mar de possibilidades aqui agora.
¿Alguna otra pregunta?
Del sistema con nanopartículas, mostraste que a medida que aumentaba el tamaño de la nanopartícula bajaba la cantidad de ciclos, o sea, la vía útil. ¿Han probado partículas estabilizadas? O sea, puede ser que estén aglomerando partículas, o por ejemplo, probaron con partículas de menor tamaño para ver si aumenta.
O problema, esses são resultados que não temos publicados. Los problemas con las partículas mayores, por ejemplo, de 400 nanómetros, es que tenemos información que es muy más difícil drenar la carga positiva del sistema. Y eso podemos seguir por fluorescencia. Porque la fluorescencia recupera de una forma mucho más lenta, que la absorción. Lo que significa que hay muchas traps positivas dentro del sistema polimérico. En cuanto contienes 100 nanómetros, esta recuperación es muy rápida. Entonces, estas cargas positivas que quedan en la estructura polimérica son un problema porque eso conduce a degradación todo el tiempo. Y creo que esa es la razón. Sí.
Entonces, esto se lo podría hacer también con la forma, o sea, con la relación volumen.
Sí. Eso es algo que es importante. Y no mostré aquí porque pertenece al proyecto de Cochrane y ese era un proyecto industrial y que no puedo mostrar muchos resultados. Pero esas son variables muy importantes y creo que chicos que están haciendo lo mismo pero con otro método de producir nanopartículas.
La foto que mostraste parece muy feliz, parece.
Y hice el vídeo. Ok, esta es la foto que mostré de las nanopartículas. Elas están agregadas a alguna fusión entre las nanopartículas, mas puedes ver que la área superficial aumenta mucho. Y eso es muy importante para tener una buena interfaz entre el material electrocrómico y el electrolito. Por tanto, eso aumenta la performance de estos materiales. ¿Okay?
Probado con partículas tipo disco o plato.
No conseguimos hacerlas. Okay. Nosotros somos completamente honestos. Nos conseguimos hacerlo así, pero no con los polímeros semiconductores orgánicos, más con este de vanadio. Porque con las nanopartículas de tungstenio eran féricas, mas aquí eran nanoplatos, discos, y el sistema aquí era muy más lento que el sistema con las ceras. Mas es un resultado que carece de investigación más detallada. Y puede ser una situación específica. Por tanto, no creo que podemos tirar conclusiones de aquí. Para hacer nanopartículas de polímeros orgánicos con una forma específica, yo creo que es un gran desafío. Porque en este caso, necesitas de tener templates para tener estas formas. Creo que la mejor opción sería a través de este método que nos estamos usando, que se llama Mini Emulsion Method. Si tú tienes una Mini Emulsion que tienes esos templates, en principio puedes formar no solo nanopartículas féricas, mas también nanofios, tal vez nanodiscos, y entonces puedes explorar un poco más eso. Mas que yo saiba hasta el momento, no hay nada publicado con eso. Por tanto, estás dando una buena idea.
Bueno, agradecemos a César nuevamente.
Para decir una última cosa, quiero agradecer a todos vos por me tener recibido tan bien aquí. Son muy simpáticos. Y sí, yo creo que voy a volver un día aquí a La Plata. No este año porque tengo que hacer otro secán, no en La Plata, más en Montevideo, en Uruguay. Pero el año que viene yo voy a estar en sabática y estoy a planear ir más 2 meses, pero no en enero, febrero. No solo por los mosquitos, más porque vosotros no toca. Voy a intentar venir y me creo marzo, abril y cualquier cosa como eso y apañar un tiempo un poco más fresco. Por tanto, creo que no será la última vez de ir aquí. Gracias.
Gracias.